Welcome to The Explainer. Okay, today we are diving into a real mathematical mystery, one where raw data is revealing absolutely massive structural alignments in our universe. We're going to be examining some truly mind-bending source material that takes millions of data points from space, completely strips away our standard assumptions, and uncovers a hidden, wildly violent physical reality. We're going to explore how a concept that's usually reserved for, fluid dynamics is literally helping us map the very center of our galaxy.
Imagine standing in a packed room where one single voice is just so overwhelmingly loud that it completely drowns out absolutely everything else. Well, that is exactly what this staggering number represents in our data. When researchers analyzed the raw momentum vectors of the galaxy, they weren't met with random static or some equal distribution. No, instead, they found an intense, singular mathematical dominance holding almost 100% of the signal's variance.
And it gets crazier when you look at the raw data. When you run the pure CAVITATION Python script and look at the unfiltered SVD spectrum right from the terminal, the data proves that Mode 1 completely dominates the whole shebang. Look at those raw Pascal values. Mode 1 boasts a singular value of over 20 million. Meanwhile, compared to that roaring primary signal, Mode 2 is just a tiny whisper. And Modes 3 and 4? They are virtually non-existent, dropping off to a variance of literal 0%. So this isn't just some minor statistical trend, right? It's an absolute mathematical mandate.
Here is our roadmap for today's explainer. First, we'll look at the 99% signal. Second, the universal squeeze explained. Third, grounding the physics toolkit. Fourth, mapping galactic cavitation. And finally, simulating cosmic power potential.
All right, let's jump right into section 1, the 99% signal.
So the crucial takeaway here is that this overwhelming 99.96% variance is not a random data error. It is a mathematically proven anisotropic alignment. When we look at the right singular vectors, which represent phase spatial coupling, Mode 1 shows an almost perfectly balanced negative weight across all four axes, negative 0.4993, negative 0.5009, negative 0.5006, and negative 0.4993. It's incredibly consistent. But as we move down to Mode 4, those inner axes drop to absolute zero. The sources conclude that an alignment this perfect absolutely cannot be explained by just a survey wedge footprint or some glitch in data collection. It points to something massive.
Moving right along to section 2, the universal squeeze explained.
To really understand what could possibly cause a signal this massive, we need to talk about a phenomenon you'd normally associate with turbulent liquids, which is cavitation. Think of bubbles forming and violently popping in a pot of boiling water, or maybe around a rapidly spinning boat propeller. But now I want you to imagine that intense physical agitation happening on a cosmic mathematical scale. We are talking about a highly localized region of space that is so agitated, so turbulent, that it physically pushes outward against the surrounding galactic matrix.
This quote brilliantly captures a core physical conflict. It's basically high internal scatter violently pushing outward against the relentless, crushing inward force of what the source calls the universal squeeze. It is literally a battle of pressures. When the outward force wins, it carves out a massive cavitation bubble in the galactic medium. And that localized pressure deficit, that is exactly what we are detecting in that 99% signal.
Okay, let's hit section 3, grounding the physics toolkit. Now, you might be thinking this all sounds a bit abstract, but we aren't inventing new, unproven physics here. We can actually ground these macro-level galactic shear zones using the exact same micro-level kinetic energy formulas you'd learn in an advanced higher physics class. Rotational kinetic energy equals 1/2 times the moment of inertia times the angular velocity squared. We are just applying these classical laws directly to the raw density and velocity dispersion of stellar bodies.
And the fundamental laws of acceleration and gravity act as our absolute physical anchor here. They let us translate super complex vectors into pure pressure dynamics. The source material draws directly on standard equations, like centripetal acceleration equating to velocity squared over radius, or the universal law of gravitation. By utilizing these fundamental laws, we can calculate the exact dynamic pressure and stress scaling going on in the substrate of space.
So why do it this way? Well, usually, looking at galactic data means trying to plot millions of separate, complex 3D directional arrows, complete with all these artificial mathematical smoothings and arbitrary grid rotations. It's a mess. But by dropping that tangled mess of standard vectors, we can map absolute spatial coordinates directly to scalar cavitation velocity for a much, much clearer picture.
It collapses all that clutter down into a single, raw, unadulterated pressure field.
Which perfectly sets up Section 4, Mapping Galactic Cavitation.
By processing our data through these specific steps, we strip away the smoothing and arbitrary rotations to uncover the raw pressure field of the medium. First, we capture the raw Cartesian momentum of every particle, or star, exactly as measured. Then, we convert that directional force into a cavitation pressure vector, which is weighted by the kinetic pressure of the medium itself. Finally, we accumulate all of those into one massive stress tensor matrix. And this matrix is exactly what we feed into our singular value decomposition.
Now, these specific metrics are a real game changer because they allow us to replace millions of chaotic star nodes with a beautifully continuous 3D scalar voxel grid. Instead of just staring at dots moving in space, we measure the physical depth gradient using inverse parallax. We measure the transverse wave shear using combined proper motion. And we can track direct acoustic compression right along our line of sight using radial velocity. Add it all up, and you get the total cavitation potential field.
And what's wild is that even when analyzing a colossal 25 million pressure nodes from CERN data, we still see an empirical dominance ratio proving the primary stress axis is the absolute loudest voice in the room. In this massive secondary test highlighted by the sources, Mode 1 held an incredible 99.32% of the energy variance. That completely confirms that this extreme spatial anisotropy isn't just an isolated fluke, it's a fundamental, defining property of the stress matrix we're measuring.
Finally, let's dive into Section 5, Simulating Cosmic Power Potential. So, what does this massive pressure inequality actually mean for our universe? Well, by taking the square root of the sum of our singular values squared, which math folks call the Frobenius norm, we can estimate the sheer power flux of this cosmic acoustic frequency. The sources explain that in continuum mechanics and wave physics, this norm tells us the maximum strain energy density stored within a pressurized substrate. We are literally calculating the stored stress energy of a galactic zone.
And check this out. Look at this specific principal shear angle, mathematically derived directly from the predictive simulations of the SVD matrix. By multiplying that stored stress energy we just talked about by the system's driving acoustic frequency, the models can actually pinpoint the orientation of the shear strain. It gives us a highly specific angle, like negative 144.52 degrees, derived completely from pure, unfiltered pressure dynamics.
So I'll leave you with this provocative thought. Are we just looking at empty space, or are we witnessing the relentless crush of the universal squeeze itself? We have a 99.9% dominance ratio pointing directly to a massive anisotropic pressure zone centered right on the galactic core. It challenges absolutely everything about how we visualize the vacuum of space, replacing it with a violently churning, pressurized medium. Thanks for joining me on this explainer, and keep questioning what the raw data is really trying to tell us.